Welcome everybody to this presentation on measuring surface displacement using a novel UAV car-borne radar interferometer, including a case study on the fast-moving landslide in Brienz in Switzerland. My name is Othmar Frey, and the co-authors of this work are Charles Werner from Gamma Remote Sensing and Andrea Manconi as well from Gamma Remote Sensing, and Roberto Coscione, who is a PhD student at our group at the Institute of Environmental Engineering, ETH Zurich. Why would we want to use a mobile mapping tool based on a car and or a UAV to perform displacement measurements with the inside L-band? We have target applications in mind, such as observation, monitoring of surface displacements, landslides, as well as other surface displacements such as glacier flow velocity. So it's clearly with a target into displacement monitoring, geohazard monitoring. UAV-borne SAR and also car-borne SAR have the advantage that they can have a long synthetic aperture. This means that we can reduce the frequency and still obtain a fine azimuth resolution when we compare that to quasi-stationary terrestrial radar systems. So the potential of such a system is to use low frequency systems such as ours at L-band on agile platforms that we have a complementary way of measuring surface displacement as compared to the Ku band terrestrial radars. And these differences are in terms of the temporal decorrelation properties in natural terrain and also the different sensitivity of the surface displacement. And in a more long-term perspective, such agile platforms could be a cost-effective and flexible alternative to manned airborne SAR platforms in the future. Here below, you see the platforms that have been using so far. So two car-borne implementations of our L-band SAR in-SAR configuration, and in the middle, one on a helicopter drone by Aeroscout. This is the L-band SAR hardware that we are using. It's a compact L-band SAR system that has up to 4 low noise receiver channels simultaneously. It's an FMCW, so frequency modulated continuous wave radar that requires a transmit and separate receive antenna. It is potentially also a full pole system. We are not using this property in our experiment here, but there's a possibility to have full parametric acquisitions as well. It's important maybe to mention here is that the resolution that we are achieving is in the order of 1.5 meter in the direction of propagation, so the range direction, with this allowed 100 megahertz bandwidth frequency that we can transmit in Switzerland. And the azimuth resolution depends a bit on how long our synthetic aperture is. If we have a full synthetic aperture, we reach resolutions down to less than 0.5 meter for typical acquisition scenarios that we've been using, where we drive something like 250 meters or so. We get range-dependent resolutions with something like 2.5 meters as a range distance of 5 kilometers. We have started to do demonstration campaigns in 2018 with this system. This is a system that we're using together with an IMAR navigation system to measure surface displacement of a glacier. I have talked about this a bit last year already in the SGM meeting. And I would just briefly highlight the measurements that we have made without going too much into detail otherwise. So this is Sustenpass area with Steinggletscher here in the background and Steinsee in the foreground. We have been driving on the pass road and observing this area multiple times over time spans up to 17 hours. And what you see here is the SAR imagery that we obtain, as well as the interferometric phase and coherence of, in this case, a 17-hour time span between the measurements. And after some trend corrections, we receive this differential phase here and can convert that into line of sight displacement map that you see on the bottom right here. Then in 2019, we have conducted the first UAV-borne L-band, the INSA demonstration campaign, with several acquisitions on 2 dates. With this campaign, we could mainly demonstrate the performance of the system also in this airborne scenario with a small drone of Aeroscout, is the manufacturer of the drone. And what you see at the bottom here is the scenery as taken from below where the aircraft was flying afterwards at the height of roughly 50 meters above ground. The antennas are directed side looking, so looking perpendicular to the direction of the flight. And here you see an imagery that we obtained with such a system setup. Then the example that you see here with the interferometric phase and the coherence is for a short-term repeat pass. So you see here that is on the same date, so the 13th of February in 2019 at 2 different times, separated by roughly 3 minutes. So of course there's no displacement to be expected in this short time frame for this scenario here. So the goal of this was just to show basically the clean phase screen that we obtain that would, if we had problems with the navigation or the processing, would otherwise be visible as phase artifacts. So the 0 phase that we obtain here is a good indication of the good system performance that we are able to actually measure displacements also in such a UAV-based scenario. Also the coherence here, which gives an indication of the quality, high coherence values close to 1, giving a high quality of the phase, shows that except the areas where we have vegetation, we have a high coherence also for this setup. So now I would like to go to the main demonstration case that I would like to present in this presentation here, which is this Car-borne L-band INSA test case at the Landslide in Brienz, that we conducted in January, February 2020. As Andrea Manconi has detailed in the previous presentation, the well-known landslide in Brienz shows surface displacements of several centimeters per week for this part that is called Rutschungdorf, and up to several centimeters per day, even in the part that is Rutschungberg, so this area that is above the village. Between the 20th of January and the 4th of February in 2020, we have conducted the repeat pass Car-borne INSA observations from 2 road sections as shown with the red lines here on the map. So here is the village of Brienz. That is the open part of the landslide, and the area affected by the landslide is covering a large area here, including the village itself and also lower parts here of the hillside. Our first road that we were acquiring is close to the Rutschungberg situation, actually taking place in the affected area, and the second one that gives a more synoptic view that is on the Kantonsstraße between Tiefencastel and Sabonin. In the upper left image, you see the setup of the measurement for this test site here. So we have a car, and on top of the car we have the L-band SAR system mounted. The yellow box here is the radar assembly and contains also the instrument computer. The quadratic patch antennas that you see, one for transmit and one for receive, are slightly tilted upwards to observe the slope of the mount. The driving direction is of course the opposite of what is shown here, so pointing the antennas towards the hillside. In addition to the radar system, we also have a INS GNSS system, a Honeywell H-Guide N580 system that is mounted also here on top of the car, close to the antennas and the radar system. You mostly can see the two GNSS antennas that are part of this INS GNSS system. I would like to mention also that this campaign is not part of the operational monitoring activities that is taking place at this location here, but it was a test demonstration campaign in collaboration with CSD engineering. And the idea of this collaboration was to further explore advanced terrestrial INSAR-based measurement systems, as well as also to test alternative locations of observations for radar observations at this test site. In my presentation, I will focus on some more technical and processing related aspects of this Car-borne INSAR campaign. So here on the left-hand side, you see now how this measurement takes place. So the car is driving on this road, observing the scenario, and the measurements are then combined in post-processing to form a high-resolution SAR imagery, and this is repeatedly done for different times. That gives then the temporal interferograms that we can use. So in the following, I will show a video, first of all, that gives you a short overview of the scenery, including the main processing chain, steps in the processing chain, and also intermediate data products that are generated to retrieve the final surface displacements from this interferometric measurements. You see in the foreground the sensor trajectory as used for this particular data set here in red. What you see now is the SAR imagery, then the interferometric phase, the coherence that gives the quality indication of the phase, then the unwrapped and detrended phase, as well as finally the line of sight displacement that is derived from the unwrapped and detrended interferogram. I also mask low coherence areas, so you'll see in the next few slides in a bit more detail what has been done for this processing. The SAR processing is directly into map coordinates. And with this processing chain, we can then directly in map coordinates take a differential interferogram. Besides the actual landslide area here, also in the back, there are some phase values that are non-zero. And this is due to also tropospheric changes. So what we like to do is to detrend this unwrapped interferometric, the interferometric phase. And we do that in this case by a robust multiple linear regression. So here on the left-hand side, you see the original unwrapped interferometric phase. Here is the part with the landslide. Everything is with respect to a reference point here that is assumed to be not moving. Then we calculate, based on this robust multiple linear regression, a trend estimate of the phase that should not include the displacement phase here, but just the tropospheric variation. We do that regression with respect to delta easting, northing, and height. And this is the outcome of this trend estimation. So you see that there is no changes here in this area, since we're just interested in the large scale trend that is not due to our signal of interest here. Then we can subtract this phase from our original unwrapped phase, and we obtain this product here, which is then the detrended unwrapped interferometric phase that we can then further use to calculate the displacement in meters. So if we map that to the ground, we see that now we have basically close to zero phase also here in the background that we assume is a phase that is not due to displacement, whereas we still keep our displacement signal here in the foreground. And you see that also with this L-band system, we are able to distinguish also a phase jump here at this edge. And if we check On site, you see that this coincides very well with the visual changes that you actually see on site, where the road has been multiple times be reconstructed to meet the two ends where we have this strong disruption here along this line that we see here in the interferometric phase. So then the final product is, in this case, the 4-day line of sight displacement derived from unwrapped and detrended interferogram. And I already whitened the low coherence areas here. So this is such a product that we can generate with this Car-borne INSAR system. So this is showing nice displacement values for the open part of the landslide, as well as also for the more vegetation covered landslide over part of the landslide over its time span of 4 days. So now this coherence threshold is something that is used in this case to kind of set a lower bound on the quality that we would like to achieve. To assess the precision of the interferometric phase, we can use the formula by Martin and Rodriguez, 1992, which relates the standard deviation of the interferometric phase to the coherence and number of looks. So with a number of look of 50 and the coherence coherence value of 0.7, we reach a phase standard deviation of 5.8 degree, which corresponds to a standard deviation of the line of sight displacement of 1.8 millimeter for our L-band system. Then, as a next step, we would like to have a look at the interferometric coherence for different temporal intervals and weather conditions. Here at the bottom, you see the last day when we acquired during quite heavy snowfall and with already substantial snow cover and not much visual sight to the area of interest. So if we look at the 14-day coherence and phase, and we do that here for the two different locations of acquisition. So on the left-hand side, you see the coherence as obtained from the measurement further away on the Cantonal Road, whereas on the right-hand side, you see the coherence and the phase as obtained from the measurement close to our test site. So this is a bit more high resolution, but should otherwise shown roughly the same quality, although they're not exactly taken at the same time, of course. The 14-day coherence phase that we show here is based on measurements at the 20th of January, where we had dry, sunny conditions, and on the 3rd of February, where we had partially light rain during the day with a total of 6 millimeters precipitation as measured in a close-by station in Thusis. So what you see here is a quite substantial loss of coherence compared to the previous example here, which is a 4-day interferogram. So over 14 days, we lose quite a bit of coherence, mostly in the areas that we are not so much interested. So the forested area back here, this is of course due to quite some changes in the vegetation over time. Also, once dry, once wet, this changes quite a bit the backscattering properties. But what is more interesting is that we also see, of course, the correlation patterns in our landslide. And if you look a bit more closer to that, with this more high resolution result here obtained from a close-up path, we see that these are mostly shapes of debris cones that are due to rockfall events. And of course, over 14 days, we have a number of events happening. So this is a accumulated coherence loss that you get for all rockfall events happening during these 14 days. We will see in the next slide over this 1 day change that we already here in this case have one event or maybe also several that happened and leading to a coherence loss. So we see here also better in the close-up area, this area here where we have a low coherence close to zero, that is due to surface scattering changes, presumably debris that has accumulated due to rockfall up here in this area, where we also have a coherence loss. If we look at the phase, we have to think of the situation here. So this is an acquisition first day, 3rd of February, so same day as the second image of the previous analysis. And the second one here is the day after, so the 4th of February, where we have this snowfall event with a total of 5 centimeters of snow, as according to measurements at this 2C station of Meteor Schweiz. We see that the phase in the landslide here is relatively stable, surprisingly stable, although we have snow cover. So that means that even though there is snow, which is a refractive medium for microwaves, there is not too much changes in the spatial variability of the phase due to that. But of course, the phase measurement have to be taken with care as soon as we have something like snow in one event and not in the other. So it's not, it's less than ideal conditions for this displacement measurements. But what we can use for sure is this decorrelation product, if you like, where we see that events have happened even though we are not able to spot them visually during such adverse weather conditions. So it's a possibility to at least keep track of some of the events that may happen. So this brings me to the conclusion of this short overview. We have successfully demonstrated that we can perform repeat pass INSAR with this L-band SAR system mounted on agile platforms, such as a car driving on the road, or also helicopter, UAV, in our case, this Aeroscout B100. And we have shown that for various surface displacement scenarios, such as this landslide in Brienz, and previously also for measuring glacier velocity, and also a test case where we're actually using a UAV to perform our system, the INSAR system performance analysis. The test cases that we've shown provide evidence that such an agile L-band SAR system can be used to monitor surface displacement in natural terrain. And the decorrelation analysis that I was showing confirms also the complementary properties of such an L-band system compared to other systems for terrestrial observation geometries. So mostly for this landslide monitoring application. The system and the data processing chain opens possibilities for more flexible observation of surface displacements over natural targets, especially targets prone to temporal decorrelation, and also we can measure such surface displacements and the decorrelation also in adverse weather conditions. This ends my presentation. Thank you very much for listening.